Hi, I'm Theresa-Marie, and I'm going to talk with you today about the process of colorizing a data visualization. And as we walk through these 5 stages, I'm going to slide in a little bit of color theory. So you get to see how to colorize a visualization, and you learn a color theory at the same time. Our first stage is to know your data. What type of data do you have? And I'm going to cover some examples. Then we're going to select a color space or a color rule to work in. Then we'll build a color scheme. Check for color deficiencies so that everybody can see our visualization. Then we're going to apply our color scheme and have some review of it, and maybe we'll modify as a result of the review. So now we're going to get to know our data a little bit. There are lots of kinds of data. There's nominal data where there's no order given, like the color of your eyes. There's ordinal data, no info on the degree of difference, but it's low, medium, or high. There's interval data, numerical values with positive, negative, or 0. There's ratio data, age, height, duration. And then there's discrete, only whole numbers, and some kind of count. There's also continuous data that we might use in a computational model. I've done a lot of computational model visualization. We have binary or dichotomous, 2 possible values, yes or no. So now that we know what kind of data is around, let's see an example. Now, for this particular example that I'm going to walk through in this talk, I'm going to use what they call a Likert scale. And that's strongly agree, you're neutral, you disagree, or you strongly disagree. I'm going to create a color scheme in magenta. We're going to go a little pink. So I'm going to have an ordinal with categorical attributes of a variable differentiated by order, rank, scale, position. That's what this type of data is classified as. And my magenta color is very precise. It's FC56FF, which you can check and Google for me if you want to while I'm talking to you. So we're going to select a color space because that's really helpful in trying to determine how we're going to apply our data visualization colorization process. So there are kind of 3 major color spaces that have been around for a long time. There's red, green, and blue, and that's what you normally see on your cell phone or on your computer laptop. There's also a cyan, magenta, and yellow key black space that we use for printing. That's what you see when you print out something or when you look at something in a magazine. And then there's the one we learned when we were in kindergarten, and lots of very well-known painters have used, which is red, yellow, and blue, which is actually mixing with paints. Now you're going to see RGB is called additive, and CMYK is called subtractive. So now let's look at color model and how, if we look at the whole spectrum of color, we create a color space. So right now I'm going to show you the color space of sRGB because that's what that little triangle in the center of this diagram, that's what you normally see on your mobile phone. And then that sort of oval circular kind of thing, that's what happens when you convert it and print it out on paper. So Adobe, when it created Photoshop, created its own model called Adobe RGB, trying to create a triangle that would encompass both. So you wouldn't have to worry about if you saw a color on your screen and then you decided to print it out. And then Kodak came along and they got into digital cameras and they came up with ProPhoto RGB. Now, what's interesting about Camera Raw, some of it you may have heard of that, some of you may have know that, is you can pick a color in the blue scale, for example, down into that triangle that you can't see. None of us can see that color. So you might not want to shoot your film using that color. Okay, there are some other representations of color spaces. One of them is hue, saturation, and value, and hue, saturation, and lightness is the second one. Now, these came along in around 1978 as computer graphics displays were evolving. And the deal was that it was very hard to work in RGB color space. Sometimes you could try to create a color where there were negative values and positive values all together. So they created hue, saturation, and value, and they created hue, saturation, and lightness. The hue, saturation, and value is an upside down cone, and hue, saturation, and lightness is a double cone to make it easier. Now, these were attempts to make it more intuitive rather than standard RGB color space. Now, the reason you might care is HSV is used a lot in terms of picking colors on your computer screen, whereas hue, saturation, and lightness is used a lot when you're designing web pages because you can specify an HSL color directly into your code that you write for your web page. Now, there's a whole nother arena called perceptual uniform color spaces, and one of them's called Munsell. He's the first guy that sort of looked at this issue, and the other one is hue chroma luminance. And I'm going to talk about more of this as we go on in this talk. So this is the actual model that you can have for hue chroma luminance. So let's talk a little bit about Munsell. Now, Munsell was an artist, and I'm going to use, in my example, a solution that works in RGB or Munsell color spaces. So the magenta is going to work in either one of these color spaces. So I'm going to give you a chance to see this a little bit further. Now, what Munsell did was Munsell was coming along and he wanted to study how people looked at color. And he came up with something very important, and that is we don't see color very well. We see in terms of like a uniform sphere. We see more reds and differentiate between more reds than we do blue greens. So Munsell had to come up with a system that wasn't geometrically uniform. So what happened was we couldn't create a really easy 3D color model in Munsell space. So when it came time to determine color rules or color harmonies, people had to accept the fact that it wasn't perceptually uniform. And I'll show you some perceptual uniform spaces a little bit later. Right now, we're just going to determine the color rule for this pink visualization I'm going to do. And what we've got here is color harmony, which is the kind of thing that artists use, which is a color wheel to provide common guidelines for how color hues work together. And then we have this phenomena called data, classifying it color schemes for data. And the three types of these are sequential, diverging, and qualitative. So it turns out we can put all this together, and I call this harmonic resolution is when you combine these two concepts together. So let's do that. We're going to look at a little color harmony history right now. I'm going to sneak it by you. It turns out that our friend Isaac Newton, he was the first person to come up with the idea of taking a color spectrum and forming a color circle as a simplified model. He thus created the color wheel for color harmony. And this is a picture of his first color wheel. And I added the little squatches of color so that you could recognize how he did his color wheel. You'll notice that he didn't put my color magenta on the color wheel. That is the color between violet and red that you'll see there. So it would not be until in the 1800s till Goethe put magenta on the color wheel. But we'll go on anyway. So now what we've got is we've got these three common ways of looking at color harmony. One of them's monochromatic. That's if you take one color, you add a little bit of white, that's a tint, you add a little bit of gray, that's a tone, or you add a little bit of black for all your colors, and you mix your colors with one color orientation, and the differences has to do with the white, the gray, and the black. Another color harmony is analogous, where we pick all these colors that are next to each other in the color wheel. Now this one's in the key of cyan, and what we have is we have a middle color of cyan. We picked all these colors next to each other. Then complementary. What do you think's the complement to cyan? It's really something like an orange. So that's complementary color harmony. Now, let's think about what would happen if we're looking at color schemes for data. This is something that Cynthia Brewer of Color Brewer developed to describe color in terms of geographic and data visualization. And she said there's sequential color schemes optimized for ordered data, from low to high. And guess what? There's diverging schemes that place equal emphasis on a mid-range critical values. Now you see, now I'm translating here. I'm telling you that sequential color schemes are a little bit about like the monochromatic ones, and diverging color schemes are like the complementary ones. Now, there's another scheme that I'm not going to talk about in this example, but it's called qualitative, where you're not interested in magnitude differences, but you just want to categorize. Like you want to note all the items that are in your kitchen, and you're just going to note them by the different kinds of pots and pans you've got. So that might be a qualitative color scheme you might use for that. Now, for my example, it turns out that I have a complementary color harmony because I remember I said I had agree and disagree. So I'm going to select a complementary color harmony where I have green, magenta and green oppose each other on the color wheel. Or I can be in Color Brewer and I can select a diverging color scheme that is also pink and yellow green. Either one is going to help me colorize my data in step 2. So that's the particular color rules I'm going to use. See, sometimes you can use 2 similar color rules and get similar results. And that's what we're going to do in this example. So we're going to move along. And look, oh my gosh, when I build the color schemes, I could get really on the pink side, or I could lean more on a sort of a reddish kind of pink, or a blushing pink here if I use Color Brewer. But you can see either one of these I could use to build my color scheme. And this is what I mean by a harmonic resolution. They both come together. So for my example, I'm going to use Adobe Color to build a 5-element magenta green color scheme with white as my neutral element. Or I can just go into Color Brewer and I can get the pink yellow option and select 5 classes of data. Now, there's one little problem I talked about is item number 4 in building a color scheme, and that is color deficiency. It turns out that there are many people in the world, not a small number, let's not say many, but there are a few people in the world that their eyes see color a little differently than people with normal color vision. Their red photoreceptor is absent. Now, it's not like being on a cell phone, so like the red display just doesn't work. It's a little more complicated. And that what they can't do is differentiate a range of colors. See, this is the color wheel here, and they have trouble seeing these colors apart from each other. So if you put a red and a green colors next to each other, they might not be able to differentiate. And we got to check our example to see whether it's going to work. Deuteranopy is if your green photoreceptors are a little absent, and tritanopy is if your blue photoreceptor is absent. So now we're going to check for color deficiency. Now the neat thing is Adobe Color has a way of using an option called accessibility tools, and you can check it. And if you look up really close, it just so happens the example I picked, what will happen is if we have a color deficiency, it'll come out kind of okay, because the person who has a color deficiency that is either deuteranopy or protanopy is going to sort of see the magenta as a blue tone, and is going to see the green as a yellow tone. So it's not going to be the same visualization concept that we had, but they can differentiate between the data elements. So that's going to be helpful to us. Now, the neat thing about this software is if they don't differentiate, it tells you. This one says everything passes just fine. I will tell you a color scheme that would not work, and that is if you had orange and green. It would be really hard to differentiate. But we don't. We're lucky we have magenta and green. And then when we look at Color Brewer tells us whether there's a color deficiency. If this eye has an X over it, oh my God, it won't work. But it does work. So for my example, we have an accessible color scheme, or something that's called colorblind friendly, if you want to say it that way. So here I am applying my color scheme, and I'm showing you here, this is what the Adobe solution is, and here's what it looks like for my particular example. So I've applied my color scheme. It's built for 5 points in Likert, and you see it's diverging, and it's magenta and it's green. For strongly agree and agree is magenta, neutral is white, disagree and strongly disagree is green. Now we're going to go back and test. I want to test it one more time with the actual visualization, and sure enough, it won't be the same color scheme that I designed, but people with color deficiencies can tell the difference between the data. Now, I want to talk again about why we care about this perceptual stuff, because I told you about perceptual uniformity early. So I mentioned to you how Munsell was out there, and he was trying to develop a 3D color model that was going to be like a sphere, sort of like a globe. Then he went out and did his perceptual test, and he found out that human beings are wired differently, and we see a larger range and differentiate between red, orange than we do between blue, green. And this is he gets this diagram, this kind of a odd non-geometric shape. Now, there's also another problem, and that is the traditional color map, the one that Newton mapped out. It has some artifacts in it. So when you're doing data visualization, if you're not careful, what can happen is you don't have a uniform distribution of your colors. You have artifacts in your color scheme that you didn't put in there. You didn't make it. It wasn't your fault. You didn't do it. So we have to be careful about that. So now I'm going to show you some example. This is the non-uniform color map. That's sort of the traditional one that has been around for a long time. Newton initially mapped it. Then would be a perceptual uniform color map. Now, this was done by hand. It's not a numerical or computational model. It's not a particular color space, but this is some way I did it to sort of smooth it all out. Now, what does this mean to you? Here's what it means. If you compare the rainbow color map in your data visualization process to other color maps, you'll see. Notice in this particular example, this striping here, right? Well, guess what? For a grayscale, there's no striping. For others, there's no striping. Then for this one, there's no striping. This is what I mean by artifacts that were put in there because of the color map that you chose, rather than because of the data itself. This slide, by the way, came from Borland and Taylor, who did one of the early papers in 2007 about data visualization, the end of the rainbow, and how people still continue to use the rainbow color map. Other recent work after their paper came out is in Matplotlib, whereas they changed the color map. Rather than using their Newtonian color map, they decided to use a Verdis color map. And you'll see this used more often today in their particular color maps as the default color map rather than the Newtonian one. So if we look at this Munsell color system that I was telling you about, it has a 3D color space from Munsell's experiments. There are 5 principal hues: red, yellow, green, blue, and purple. Now to get that 5, what he did was he got rid of the orange. Artists for a long time had 6, and Munsell got rid of that orange and just sort of created, because he wanted 5 elements that if you multiplied by 2, you could get 10 steps, and then you could increment it up into 100 hues. So he came up with his value. His black is a 0 value at the bottom of the scale, and the white is 10 at the top. And then he measured chroma out radially, and this is where he got really wild looking for him, because the chroma is where all those values started differentiating between perceptual experiments. So people celebrate this guy's contribution because it was actually very important. But this is why you don't see a spherical model of color. You can make it, but it's not how we humans see. So this would be at level 5 on the Munsell scale. This would be the perfect color model. But we're not at level 5 frequently. Sometimes we're at 6, and we're at maybe 18 if we're in red-green mode. I mean, red-orange mode. And then I told you blue-green mode. So this is the diagram I was telling you about earlier, these combinations. And if you really want to study them all, there's a site. Andrew Rife, he put color, the Munsell Atlas color online if you want to look at this. It's freely available to you if you want to go out there and study it some more. Now, there is another space that came after Munsell's time called CIE-XYZ. And this was an effort to put all the colors like in a horseshoe type shape and sort of to display the color to space independent of the type of device that you had. So the idea was being you could use this to calibrate printers or displays. See, it turns out that my phone is probably different than your phone with regards to its RGB color space. But if we use CIE XYZ, we could have it all calibrated, and we have a uniform color space that we can talk about. Well, how did they get all this data? Like, how did Munsell and this guy, David Wright, get all this stuff? Well, what they do is you and I go in and say, okay, I'm willing to participate in this study for color matching. And they calibrate us to see whether we have a color deficiency, because if we have a color deficiency, they're not going to let us. And then if it turns out we pass some other sort of test, we become an observer. And then we are asked to match a particular color. So for this one, we're going to shine a yellow light in our eye. And then we're going to be given some little knobs of red, green, and blue. And we're going to match that color as best as we can. And that's what all this data is built on. Kind of interesting, isn't it? I just want you to have a background of what this data is about when we talk about observers. So this is the chromaticity diagram I was telling you about earlier. All visible colors for the human eyes are in this sort of horseshoe. The edge of the diagram is called the spectral locus. The least saturated colors are at the center. There's always a region of white at the center of one of these chromaticity diagrams, and you can see we have our center of white. And 2 colors along any given line between 2 points are made by mixing the colors at the endpoints. So let's look at our line of purples down there. If we take a blue and a red together, we can make that magenta color that I like. So that's the line. Well, guess what? After all of this, it turns out that XYZ is not perceptually uniform. Nope, it's heavy on the green side. You can kind of tell up top here, there's more green. See those? If those ellipses become circles, it's uniform. But you see how these ellipses, they're not circles. So David McAdams showed that these ellipses are defined visual distortions. So the color space isn't uniform. Oh no, we got to go back. Well, then in the 1970s, they updated this and they came up with 2 of them. One of them is CIE Love, and it is a color space, and you can see it's got much more blue in it. But remember, I reminded you, I told you that we're not surprised. Munsell had already told us about this. And then there's another one that's based on what they call opponent color theory. Opponent color theory is based on the idea that lights, now don't think paints like you did in kindergarten, but lights. So if we go out into the world, we don't see green or red light, kind of together. It doesn't work that way. And we don't see blue and yellow light together. And you know why? The reason is red and green light, when it's combines together, makes a mess. No, it makes yellow. It makes yellow light. So that's why we never see them combined together. And blue and white light, guess what? If you put them, if you put blue and yellow together, I gave it away earlier, you're going to get white light. Why? Because we've already figured out that if we have red, green, and blue, we'll get white light. So if red and green makes yellow, yellow and blue is going to make white light. Oh my goodness, that's opponent color theory. And CIE Lab is based on that kind of concept. So if we look at the transitions of color chromaticity diagrams, we can see that we moved from a much less amount of green in the color space in CIE LUV. So now, those were perceptually uniform color spaces, the lab and the lab. But they were also shown to have some difficulties too. So it turns out the best one right now is if instead of Cartesian coordinates, you go to those cylindrical coordinates like they did for HSV and HSL. Well, now we're going to go to cylindrical coordinates and create hue chromoluminance out of CIE Love or CIE Lab. And this is considered the closest to perceptual uniform today. And it's begun to being used by visualization people who use the R programming packages, the Python, and the D3. So some visualization practitioners prefer this particular color model. Now I'm going to show you what is it that Theresa-Marie's been talking about. Well, here's your RGB color scale. Here's down here we show the color band, and then if we take it into black, you can see those artifacts I was telling you about. But look, HCl, when we take it into grayscale, black and white, look, it almost is uniform all across, and that's perceptual uniformity. But just because something is perceptually uniform does not mean that it's going to pass color deficiency. Because what can happen is still someone who has a color deficiency might not be able to differentiate the colors in your color scheme. And here I show you the difficulties, that there are going to be some regions that if you have two colors that are next to each other, that the person who has a color deficiency can't tell the difference between them. So here we're going to look at HCl Wizard, which is a tool for hue chromoluminance that you can find online. And we're going to pick a color scale using that tool and see if we can get one that's a little bit like what we had earlier. So they have a palette creator tool for sequential diverging and qualitative. We already learned that in Color Brewer. And then you can export those color codes into hex and RGB codes. Hex, by the way, is what a web codes are. And then I'm going to show you the example visualization option. See how it has a bar chart? So we can kind of look at and see what our bar chart, it's a little close to our Likert scale. So here it is. I'm going to build my color scheme using HCl Wizard. I'm going to do it all over again. And I'm going to check for deficiency. And sure enough, the results are similar. It would be really scary if the results were different than what we got before. But sure enough, it can pass the color deficiency test. And then I'm going to apply it to my data, my Likert scale. Looks a little similar, doesn't it? So we've got red, magenta, and green diverging color scheme with the 5-point Likert scale. Strongly agree, agree, neutral, disagree, and strongly disagree. And I've showed you how to do it 3 different ways. So I talked about 5 colorizing steps. Know your data, select your color space, build your color scheme, check for color deficiency, apply your color scheme. And then I did it 3 ways. I did a complementary color harmony. I did a divergent color scheme like in Color Brewer. And I did an HCl, hue chroma luminance combination. And you can see we get similar results across the board. So there are many more mysteries when it comes to color. And I wrote a book about it. I loved it so much. And the book is called Applying Color Theory to Digital Media and Visualization. And I cover a lot of different apps in that: Adobe Color, Pantone Studio, Color Brewer, Color Scheme Designer, if you want to learn about it further beyond this talk. The one I cover today, HCL Wizard, is not in my book. I did not cover that. I was not looking at perceptual uniformity when I wrote the book in 2016. So you got knowledge that I don't have in my book. But I do cover Color Brewer, and I do cover Adobe Color. And by the way, Adobe Color is what I call the grandmother of color tools. It's been around probably the longest. It used to be called Adobe Cooler, and now it's called Adobe Color. Okay, so I had a fun time talking with you today, and I hope you had a good time learning how to colorize data. I also actively write on color for Nightingale, the Journal of the Data Visualization Society. See how I'm in my pink magenta dress? Just to match my color scheme. Anyway, I want to thank Georges Hattab and Mary Alvilas for thoughtful edits for my Nightingale writings. And if you want to follow my latest thoughts on color, you can follow what I've got in Nightingale. I also want to thank many colleagues and family members who have encouraged me to explore color over many years. And I want to thank all of you for listening to me in this keynote talk. I hope you have a wonderful conference.